Hello guys, welcome to the lecture on one-dimensional wave equation which comes under the module number 3, that is partial differential equation, under the subject 18 Mat 21 advanced calculus and numerical methods. So in this lecture I am going to discuss about the one of the application of partial differential equation, that is one-dimensional wave equation. So to derive an one-dimensional wave equation, so we must have the figure as shown here. So to get a wave, I am taking an elastic string to get a wave after expanding it, and I am going to fix this string in the XOY plane as shown here. So I am fixing one end of the string at the origin and the one more end of the string at the point A on the direction perpendicular to the x-axis. So now in this string I am choosing 2 points P and Q having a distance delta x. So we can say that the mass of this particular part of the string will be m into dx. I can choose. Okay, the mass of this particular string will be m into dx with an angle alpha and beta at the point P and Q with the tensions T1 and T2. So these tensions are obtained by using the tangents drawn at the point P as well as Q. So here we can observe that the tension T1 is in the positive direction, so I can take it as plus T1 only, and see here we can see that T2 is going in the downward direction, so it can be treated as negative while solving the derivation. So now we can observe that the distance between the origin to point P will be x, and the distance from origin to the point A will be x plus delta x. Since the point P to Q will be delta x, we are having distance. So I can get the distance between O to Q will be x plus delta x I will be having. So now consider a small transverse vibration of an elastic string. So since as I told that I am taking an elastic string as I told in the figure of length t, which is stretched at the 2 points origin as well as in the point A also. So as I told here, I am fixing the string at the origin point as well as at the point A. So now in the equilibrium position, OA as the x-axis and the line through the origin 0 and perpendicular to the x-axis as the y-axis. Okay, so now let me choose 2 points P and Q be the 2 points on the string. Let alpha beta be the angles at P and Q. So as I told, like here I am choosing 2 points on the string PQ with an angles alpha and beta. So let T1 comma T2 be the tensions towards the point P and Q. So here I drawn a tangent at the point PQ. So this tension T1 will be at the point P and this tension T2 will be at the point Q. We can take it. So now since if there is no motion, so initially the motion will be 0. So because I am not disturbing the string at all in the initial stage, so I can assume that there will be no motion in the initial stage. So I can get the equations like this: T1 cos alpha is equal to T2 cos beta is equal to Tt. If there is no motion on the string, I am going to call it as equation number 1. So let m be the mass of the string. So let small m be the mass of whole string, but I am taking a small part of the string with the distance of PQ. So where the unit length of the string, the mass of element of PQ will be m delta x. So since I am taking a small part of the string PQ in the entire string, so I can take the mass like m into delta x like this. So in the vertical transverse direction, the components T1 and T2 are minus T1 sine alpha plus T2 sine beta. I can take it. Call this one as some equation number star. So because this equation I'm going to use to derive an one-dimensional equation, so I'm going to call this one as some equation number star. So by the Newton's second law of motion, we have the formula like F is equal to ma. So where F is nothing but force, m is nothing but mass, and a is nothing but an acceleration. So, and according to the derivation, I have the force like minus t1 sine alpha plus t2 sine beta. So in the vertical transverse direction, for the components t1 and t2, I'm having the force like this, that is minus t1 sine alpha plus t2 sine beta. And for the string pq, the distance pq, the mass will be given by m into delta x, and the acceleration is given by dou square u by dou t square I'm going to take. So now I'm going to incorporate all this force, mass and acceleration in the equation number 2. So I'll be having the equation like this now. So t2 sine beta minus t1 sine beta is equal to, t1 sine alpha is equal to m delta x into d square x by dt square. We can have, d square u by dt square will be having. So on dividing the entire equation here with the cos alpha, so since t2 is given by, so from this equation, from the equation number 1, I can take a t2 is equal to t by cos beta, and t1 is equal to t by cos alpha. I can write it. So I'm going to replace those conditions here. I'm replacing t2 as t cos beta like this, and t1 as t cos alpha will be equal to m delta x dou square u by dou t square. Since sine by cos will be tan, I can replace it as tan beta, and sine alpha by cos alpha will be tan alpha. I can replace it as tan alpha. So I got t, the tension t tan beta minus tension t tan alpha is equal to m delta x dou square u by dou t square. So now I can write the equation like tan beta minus tan alpha is equal to, since I'm taking t common factor here, I'm shifting the t to RHS, like m into delta x by t dou square u by dou t square. Call it as equation number 1. So here one thing we can observe that the tan alpha and tan beta are the slopes of the at the points P and Q. So according to the figure, the slope will be there at the point P and Q with the tension T1 and T2. So since here we can observe that for the angle alpha and beta at the point P and Q, the tan alpha and tan beta will be represents slopes at the particular point. So I can replace tan alpha is equal to dou u by dou x at x is equal to x. So because at the point P, the distance between origin to the point P will be x will be there. So I'm taking at the point x only, and tan beta will be applicable for the point Q. So here it will be given by, slope will be given by dou u by dou x is equal to x plus delta x. So since the distance from the origin to the point Q will be x plus delta x, I'm taking like this. So now I can incorporate both this tan alpha and tan beta value here. So I'll get the equation like dou u by dou x x plus delta x minus dou u by dou x at x is equal to m delta x by t dou square u by dou t square. I can shift this delta x to LHS. I got the equation like dou u by dou x x plus delta x minus dou u by dou x at x divided by delta x is equal to m by t into dou square u by dou t square. So I'm going to apply the limit delta x tends to 0 on both the sides. So since the element delta x is too small, so I'm taking like limit delta x tends to 0. I got the equation like limit delta x tends to 0 dou u by dou x x plus delta x minus dou u by dou x at x divided by delta x is equal to m by t into dou square u by dou t square. So from the concept of from the basic concept of differential calculus, we have this is a formula for the derivative. So I can replace this whole thing as nothing but dou square u by dou x square we can replace. So this is a formula for dou square u by dou x square from the basic definition of the differential calculus. So I got the equation like now dou square u by dou x square is equal to m by t dou u by dou t, or dou square u by dou t square is equal to t by m dou square u by dou x square. I am replacing this t by m as some constant, that is c square. So d square u by dt square is equal to c square into dou square u by dou x square is the required one-dimensional wave equation.